when we came up with our 3D architecture design, the first time I did the numbers, I had to go back and recheck every number 4 times, 5 times over, because the benefit we were getting in terms of geometry was some 10-15,000 times. And worked on it, only to realize, yes, the geometry works. And we were thinking in terms of so current flows through metals in batteries, and we were thinking in terms of metals, like 10,000 times better, 15,000 times better. Realize that we don't need metals. You don't need copper in the battery. You don't need aluminum in the battery. If your advantage is 15,000 times over, you can get rid of all the aluminum, all the copper, and say that the carbon is sufficient to move current and still be 10 times better.
Hello and welcome to another episode of Speciale Focus, where we explore the frontiers of India's deep tech ecosystems. Brought to you by Speciale Invest, a leading early-stage deep tech VC firm in the country. I'm Hari Arakli, and in this episode, we explore the frontiers of energy storage with Apoorv Shaligram and Uttam Kumar Sen, the founders of Bangalore-based Ather Energy. Their journey began over a decade ago at IIT Bombay, where they set up a pouch cell lab at a time when all they had to go on the topic were a couple of YouTube videos, and those were elementary as well. It was also a time when they had to dismantle doors just to fit the machinery into their university corridors. Later, after stints in the industry, further honing their expertise at industry leaders like Ather Energy, Apoorv and Uttam reunited with a contrarian realization. While a lot of work was going on in battery chemistry innovation, the secret to breakthrough performance might lie in the physics and the architecture of batteries and cells. This led to their 3D electrode architecture, a honeycomb design with interlocking pins and hexagonal cells to slash internal resistance and heat generation. They have also eliminated the need for traditional copper and aluminum foils. In this episode, the two founders also discuss their modular automated manufacturing lines designed to match the rate of growth of the Indian EV and renewable energy markets. From rethinking safety with ceramic separators to scaling the next generation chemistry agnostic architectures. Join us for an insightful conversation about rethinking the battery from the whiteboard up. Thank you, Apoorv, for doing this. Welcome to Speciale Focus, Uttam, Apoorv. The plan is to have just a conversation to bring not just the startup ecosystem, but also wider audience, a sense of the deep tech innovations that you are working to develop and commercialize. So I was thinking that it might be interesting to go back to what you said, Apoorv, last time we were talking about how when you both started setting up the first pouch cell lab in IIT Bombay, things were very, very different. And I just wanted you both to reminisce for a few minutes about that and how little folks understood some of these things. And then we can come to the truly sophisticated stuff that you are now, developing at Eternal.
Uttam, you want to start?
Yes. So I think that is almost more than 10 years back we're talking about. It is like 2013, 14, 15. During that time, we have started working on pouch cells. Back then, I think it is only the metal research at the academia. That is what we know about. And that is what is happening in India as well. There is no know-how, no knowledge were available on anything which is beyond coin cells. So coin cells is the form factor which is used for any kind of academic research. Like a few milligrams of material goes in, few ampere hours, that is what we are getting from that cell. But beyond that, whether it is pouch cell, whether it is cylindrical cell or any other cell, those are going to be few thousands mAh. Okay, that means at least couple of ampere hour cells. That means you have to have like a bigger electrodes. You have to process a lot of material. You have to make a bigger cell out of it. And then all the formats, all the processes, all the formats, those are like practically unknown to us. Okay.
If it reminds me that when people in academia work on materials research, material synthesis, the typical size of the amount of material that is made, say in one trial, tends to be like a tenth of a gram. And there I was when I joined this research group, and we said, okay, we want to make pouch cells. We're setting up lines for this. And I used to walk into the room and say, we should make at least 50 grams of material and then make a slurry out of it. And people used to look at me as if, I'm some alien who walked in, I mean, what are you talking about? I mean, it takes us so long and so hard to make 1 gram of material. And here you're just coming in saying, no, we'll make 100 grams of material. And if it's waste, it's fine. Because it's a trial, we have to understand, we have to study, and there will be some wastage. So it was very different days. It was very different environment because we did not have focus on building devices, building prototypes, but more towards the fundamental research and development. What's the new chemistry that can come about? I think I mentioned to you last time as well, right? When we had to make cells, and we had to make these realistic cells. How do you do it? How do you scale things up? What's the process used? What kind of machine is used? There was no know-how apart from maybe 2-3 YouTube videos.
Yes, and those YouTube videos are also very basic. Okay, there is not much information out there. Unlike today, if you open, if you go to YouTube and if you want to learn how you can make a lithium-ion cells, not for the commercial application, not to that high grade, but if you want to make at least maybe if you have like small lab facility, if you want to make lithium-ion cells and if you have access to all the materials, you'll be able to make it. If you are like not from this background, still you will be able to make it because there are a lot of information available in YouTube or other media. But back then, I think there is very few, one or two, that is also not like having all the information. The other thing about the equipment, when he said, that this much of material we have to produce and then we can make a pouch cell. That is one part. The other thing is the equipment. Okay. A professor wanted to have this pouch cell facility. Then there is a project from where we got the funding. Then we ordered the machine. Okay. I think Apoorv was shortlisted. He talked to the guys in China. That time, what kind of machines are required, what are those specifications, that is also very much unknown. But he figured it out, and at a low budget, we got the machines, whichever is needed. When the machines come to the facility, okay, we are seeing that kind of machine for the first time. Okay, it is not the complexity, it is the size. Okay. At academia, what we have seen is a small benchtop machine, half manual, okay, or mainly like manual. You can do by your hand, and all those things can be a benchtop. And the lab arrangement are also like that. If it is a small room, all the wall side there will be lab counters, and on that we will make those cells. Okay, or do whatever work we have to do. But these machines need big space that should be on the floor. Okay, generally when you design the lab area for academic, it is mostly the lab counters. We do not keep floor area open. It is only for the working purpose. Now that's a big machine came. It has to be kept on the floor where we are going to get those spaces. So what we have done is we have the corridor area. We have make arrangement on that. We have like a built wall, which is again very difficult to get the permission for that because it is supposed to be the corridor. But somehow we got the permission. We spoke to the engineer that we need it. We have those machine. It has to be placed somewhere. We like a build wall around the corridor. We get like a decent area, and then we started stationing those machines over there.
In fact, I remember that when that machine actually came in and it was unloaded from the truck, we had to dismantle a couple of doors just to get those in.
And you would be using this machine to make what exactly?
Those machines were used to make small format coin cells. Small format pouch cells, which is basically how much I'll say like
like 1 or 2 ampere hours. It was if you remember the battery cells that used to go in the old Nokias, right? Those small around 1 or 2 inches,
3 inches,
2 inches
by
or
3
2 inches or
inches.
so.
And were those the kinds of applications for the batteries that you tried to make?
So back then, I mean, so this was meant for trials for early trials into making devices that can be used as storage for solar applications. So eventually these cells would have become larger. But it was because it was a first step, it was like a baby step towards making these devices. It started very small. These cells were meant to be made for solar applications. Again, early steps into how we can create storage devices for renewable energy. So this was primarily for a project on solar energy. And so yeah, I mean, we started with small cells, right? Of course, for grid scale storage or solar storage, you need larger battery packs made from larger cells. The idea was, okay, start small, figure out how the technology works, how the fabrication works, and then eventually move to the larger cells. Some of the machines were actually common. You can use the same cells, the same electrodes, and you cut it to different dimensions and you start making different sizes of cells. Sometimes requires some tooling changes to the machines. But I mean, it's more of a sort of a flexible approach to making different shapes and sizes of cells. So that's actually one of the advantages of pouch cells.
This was while you guys were in your master's course for research?
I had just finished my master's, had come back from the US. Uttam was finishing his PhD.
Okay.
So it was like during my last year of my PhD. Okay. I completed my PhD early 2015. Okay. Like before that, all my like PhD related requirement has been fulfilled. So 14, 15, I was working on in this project. Yeah, so that is basically the last year of my PhD.
And before starting e-TRNL, did you all spend time in the industry or jump right into starting e-TRNL? How did that work out?
So, I mean, post IIT Bombay, once we set that lab up, we actually developed the technology, the process to make pouch cells. And post that experience, both of us joined Ather. So we were part of Ather's early cell team. We actually set up that early cell team. Worked at Ather for, I worked there for 2 years. Uttam worked there for almost 5.
So I worked there for 5.5 years. And about joining, I think I submitted my thesis on, if I remember correctly, it is like 13th of Feb. And then I joined, I think 13th of March, I think, and then joined Ather on 17th. So there is 4 days of gap, and then I immediately joined. From there I worked for almost 5.5 years at Ather, and then moved to Log9 Materials, where I have started their supercapacitor line. Okay, that is also started from the scratch, getting those lab ready, setting up the equipment, setting up the processes, and then started getting the initial result and then optimize it. Okay, it was like almost 11 months I was there. and then mid 2021 when we started this Eternal Energy.
So for me, it was after Ather spent some time trying to retrofit cars, take petrol vehicles and retrofit them to make them electric. Actually got it working technically, not so commercially, because did not make sense for people to have the same old car, but put the battery in it, which probably cost as much as a new car. So from a financial perspective, it did not turn out to be a project. But I mean, we managed to actually convert IC engine cars into electric. Post which we realized that, and I mean, want to work more on this. We actually worked on building an electric motorcycle. That was until 2020. 2020 with COVID and everything, there were too many disruptions that happened. And that's actually after which we started, got in touch with Uttam again. One thing led to another, we started Eternal. But of course, I mean, like when Eternal came about, it was a combination of experiences from multiple different backgrounds, right? So in grad school, I had worked on cell designs and cell architectures. Uttam had worked a lot on chemistry. We had worked together on building pouch and cylindrical cells together. And then, I mean, his experience also came from, setting up lines for something like supercapacitors, which is similar to batteries, but different in very, 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 very fundamental ways. Whereas when I was trying to build that motorcycle, had a lot of learnings which were presenting a different viewpoint as compared to when we used to work on cells, right? So when you're working on cells, you are looking at it ground up, right? Whereas when you go to the other side and now you suddenly start to understand, what do I need if I want to make a great motorcycle battery pack from cells? And suddenly the perspective changes. And that's actually what was probably very, very important in putting together Eternal, because now we were not thinking of it just from a cell designer's perspective or a material scientist perspective, but also from what do my customers require.
How did the two of you zero in on the idea of cell architecture as what you want to develop?
Multiple reasons for that. So one of the reasons is chemistry is a very long, hard game, much longer and harder as compared to, fabrication, design, and manufacturing. So typically, design and manufacturing is a hard game, right? Chemistry tends to be a lot harder simply because you're actually going into the unknowns. It's not that someone else has done it and we want to replicate it. It is more about, trying to find something new, not knowing whether it exists or not, and then going after that result. When it actually we get proof that it works, then the actual the commercial journey starts, where you have to scale things up, make sure that the processes are scaling up, the supply chains are scaling up, manufacturing actually happens. It tends to be a long run game. When we started Eternal, this was in 2021. We knew that if we have to do this in India, there's not going to be an ecosystem backing it for 10 years running. So there needs to be something that comes in a lot faster. And that's where we said, probably we focus on manufacturing of cells. Then again came the other side of it, which was, if we set up cell manufacturing, how are we going to do that? Is it going to be the same as what everyone else is doing? If so, how do we stand out? How do we differentiate ourselves? How are we going to match up to the competition, especially when the competition has orders of magnitudes of advantage in terms of the scale they have already achieved? The other side of it was, everyone thinks, and I think in our first conversation we had spoken about it as well, where, lithium, we don't have lithium. What are we going to do about material supply chains? What most of us don't think about is we don't have the supply chains for machinery as well. We don't have the know-how about what machine is to be developed and how, right? So we are not just dependent on the raw materials for manufacturing, but we are dependent on the source of plant and machinery for manufacturing itself. How do we overcome this roadblock? Because maybe I succeed, maybe I get to pilot stage. What happens if I'm not able to scale up? Right. And that was one big challenge. So there was one aspect, we wanted better cells, I mean, from the motorcycle experience, from the cell development experience, from Ather's experience, from IIT Bombay experience, we have to make better cells. But we also have to make them in very large numbers, and we have to make them very economically. How are we going to solve that problem? That problem statement is actually what led to Eternal.
So, a couple of points just want to add here. That is during the COVID time. Okay, the second wave of COVID is happening, and we had a lot of time to discuss about what is happening across, across the ecosystem. Okay, particularly on the cell side, and there are a few companies who have already announced their plans. Okay, or they have started putting some of the information what they want to do in the public domain. And like being in the early in this field, and we also have like a lot of friends who are working in the different places. So when we during those time we got a lot of time to discuss what is happening. Okay, the one thing we realize that Apoorv already mentioned is that if we start making the cells the same way what China is doing or any other country is doing, it would be very difficult to beat them in terms of economics. That is the first. In terms of performance, because they are kind of like a decade ahead than us. They have like a decade of experience than what we are starting right now. The third one is, even if we meet those performance parameter, still it is not sufficient what actual industry demand for the cells and the kind of cells that is required for EVs. It has to be much more than what is available right now, or even what is projected in next couple of years. Be it performances, be it its fast charging capability, be it its safety requirement, energy density requirement, or the kind of the scaling up happening. Okay, even they are scaling up at a faster rate, but still the demand is more than what it can be scaled up. Because it takes long time to set up factories. It's required a lot of capex to set up those factories. Then if we have to solve all of it, we need to start thinking from a blackboard, from a whiteboard perspective. So we gone to our whiteboard. We started discussing what is happening, what is needed. First, describe what is needed and what restrict the present cell to achieve those parameters. Then we gone deep into the scientific and technical details of it. What is the source of this particular problem? And then figure out, okay, this is the problem. We have to solve this particular problem. It is not the manufacturing, it is not the technology. It is how to solve this technical challenge. And that is where I believe Eternal started.
So, I mean, just to add to that, right? I mean, there were so many problem statements, and when we actually started putting our heads together, that's when the realization happened is that like 99.9% of all the work that's going on batteries is on chemistry. And the assumption is that the physics is already optimized for, which we very quickly realized that it's not. There is a large room to play in improving the physics of batteries. And that was the starting point of, let's focus on architecture, let's focus on design, and then let's focus on manufacturing. Because I distinctly remember, I think first or second conversation I had with Uttam, let's start something. Uttam mentioned this, if we do this has to be something that translates into scale and translates into a product that has an impact across the market. It cannot end at, we made a great product at lab and it stopped there. So manufacturing and designing for manufacturing was kind of built into the psyche, into the thought process from day one. So it was the idea that, yes, people are not tapping into how to improve the physics of batteries, into the engineering and design of batteries. And then, but like also the manufacturing side, the economics of it. The manufacturing also has multiple challenges, right? Most people don't realize it. I mean, we tend to talk about economics because, that's where China excels greatly. But then there is challenges in terms of quality, in terms of reliability, in terms of, the kind of land use, the kind of water use, energy use that goes into, setting up manufacturing, and how can we make all of that efficient as well. So, that was also a thought process, part of the thought process that went on early on into setting up Eternal.
Can you both talk about what is the opportunity in improving the physics of the cells? I mean, what you actually found out was contrary to belief. Not much has been done on the physics of the cells.
Right. So there are a few things that the world pretty much well understood. Right. So if you ask any battery engineer across the world, whether it's on the cell side of it or the battery pack side of it, they all understood that heat and high temperatures were the reasons why batteries were failing. Right. But the answers that people were working on when it came to heat and temperature is on the cell side of it. People were working on building better chemistry that is resilient to temperatures. Whereas on the battery side of it, people were saying, okay, if it heats up, we cool it down. Right. What people were not looking at is this the way we are making cells today? Is it the best design when it comes to the generation of this heat? Can we change the design in such a way that less heat is generated? And that's a fundamental solution, because otherwise the chemistry was working fine except for heat, except for temperature. Now, instead of developing a new chemistry, which we do not know how it works, if we make a cell that does not heat, my existing chemistries work perfectly. My existing battery packs work perfectly. People don't have to put additional cooling systems on top of it. And cooling systems can be very, very complex. There's a lot of engineering that goes into it. There is a lot of cost, weight that goes into it. And essentially what we are saying is, the whole idea of EVs is that it's a simpler system. There's a battery, there's a motor, there's some electronics, and the vehicle works. You have less parts. Now, the moment we start saying that, okay, we have a cooling system on top of it, is it an active or a passive cooling? Is there liquid involved? We have to manage the flow. You have so many other things that start requiring maintenance. That can be potential failure modes. So all that adds to complexity. Can we remove complexity? That was the thought process. Now, again, some of the work that I had done in grad school was focused towards architectures. I think I had mentioned this previously as well. I mean, I had a very unusual introduction to batteries, where I worked on architectures before materials, whereas most of the world actually works on materials. And when you're introduced to it from that viewpoint, you tend to think of everything in terms of materials and chemistry. I was introduced to it from the architecture viewpoint. So I always thought in terms of, is this the most efficient way of making use of the materials and chemistry available to me? Right. And that contrarian viewpoint actually played into it, wherein, we have to work with the best chemistry. Yes. But we also have to make best use of that chemistry. That's where it came in. And just to specifically point out the areas what we looked at in terms of improvement, existing batteries had very long current pathways. Okay, heat is very simple. Heat is the energy that you lose from going from one point to another when the current is flowing in any system. If I take a cylindrical cell, and then like when we started working at Ather, the most common form factor was 18650, which meant that it was 18 mm diameter, 65 mm in height. If you took an 18650, the distance from the negative terminal to the positive terminal was 65 millimeters. But the path that the current was taking from the negative terminal to the positive terminal was probably 65 centimeters. That's 10 times longer, right? Anyone who looks at it at this design and thinks of it from a point of view that, current's taking 10 times longer pathway, it becomes obvious that, here's the inefficiency. If it could take the same amount of distance, I would have 10 times less heat. And you go and ask any battery engineer in the world, would you take a cell that heats 10 times less? And the answer would be yes, in a heartbeat, right? Because that's the biggest problem everyone's facing. Now, can I change the design in which, let's make it not 10 times, but maybe, can we break down the pathway to 100 times? What can we do? What can we do in terms, make this even far, far superior, right? So, I mean, like when we came up with our 3D architecture design, the first time I did the numbers, I had to go back and, recheck every number 4 times, 5 times over, because the benefit we were getting in terms of geometry was some 10,000-15,000 times. And worked on it, only to realize, yes, I mean, the geometry works. And, we were thinking in terms of, so current flows through metals in batteries. And we were thinking in terms of metals, I mean, like 10,000 times better, 15,000 times better. Realize that we don't need metals. You don't need copper in the battery. You don't need aluminum in the battery. If your advantage is 15,000 times over, you can get rid of all the aluminum, all the copper, and say that the carbon is sufficient to move current and still be 10 times better. And now you have two advantages. You have one wherein you are saying heat comes down. But on the other side, you're saying, two very, very important supply chains. Copper in terms of strategic value is as important as lithium today. If we can get rid of copper, I'm reducing weight. I'm reducing supply chain. I'm reducing cost. And I'm actually getting better performance. That was the point where we said, okay, this design really, really makes sense. Now we have to break our heads open and say, how can we manufacture this?
So, from the starting of e-TRNL to today, can you give us a sense of where you are at? What have you already done and what comes next?
Mm-hmm. So, early on when we started off, we had this very clear idea of what design we wanted to work on, what chemistry we wanted to start off with. And our thought process was, we're going to need some machines to actually get this done. I would say when we started off, we probably overestimated ourselves a little bit. We thought that, these would be manual machines and we'll get cells working first, and then we'll have to focus more in terms of manufacturability and machines. The journey panned out slightly differently. When we went about it, we realized that manual machines are not enough. We don't have enough precision. We do not have enough accuracy. A lot of times, start and stop operations were very manual, which meant we did not have consistency in getting the results. And a part of the journey started where we started building our own machines, which were more and more precise or required automation to achieve the accuracies that we were looking at, the control that we were looking at, and the consistency that we were looking at. So it took us, I think, a year and a half from when we started building our first machine to the point where we got fully automated machines, lab scale machines, single individual machines, but fully automated machines, wherein, these machines worked on one single button press. Everything was coded in. It did exactly what we wanted. And there was no human intervention except for pressing that button. Place a sample, press a button. So that's actually how we thought about it, because, when we were building these machines, we started to realize, this is the basis of how manufacturing would look like. And if we have to make any changes to machinery design, it has to be today rather than after we finish the product and go to manufacturing, because the cost of that design change suddenly starts to inflate up the later we make it. Right? So that is how we took that journey, went about building these machines, optimizing the processes, as well as optimizing designs to a certain extent. I think today where we are is we are having cells that are working, cells that have shown certain amount of performance. Of course, looking to optimize it further, but then we started making smaller cells rather than larger cells. This was also something that was driven by the availability of capital, because for us it was very simple. Unlike the traditional ways, you make a smaller cell, you spend less on machines, you spend less on tooling, you spend less on machining. If we wanted to do a larger cell, we would have to spend proportionately more in terms of tooling and machining. And there are iterations, right? So if one set of small tools cost me say 2 lakh rupees, and I have to iterate it 10 times over or 15 times over, that's 20 lakh rupees, 30 lakh rupees. But the same thing if I did on a larger format cell, and it was going to cost me 2 crore rupees an iteration, I mean, there was obviously no way we could have done it. So we took that pathway saying that, optimize everything on small formats and then move towards larger. So today we are at a point where we are looking to move towards the larger formats. In parallel, what we're also looking to do is we've built these beautiful lab machines, extremely small, compact lab machines. The entire line would fit probably on like a regular dining table. What we are looking to do that now is integrate all of these, because as part of R&D, we had to optimize each and every step of the way. So we needed separate machines. But as part of manufacturing, everything, once all the parameters are set, everything is fixed. You need the machine to be as compact as possible and as efficient as possible. So what we are working towards is integrating all of it into single modules. Modules that are fully integrated, fully automated from step 0 to step n. There is no human intervention involved. And then the concept of modularity, that was also something which was our answer to the economics of manufacturing. Because, the traditional way of making cells, you have to set up very large factories to achieve economy of scale. That's why we have gigafactories. One of the reasons is, yes, we have a very large demand. But large demand could also have been met with thousands of small factories. Instead, we have very, very large gigafactories today. That's because it's the nature of the process, it's the nature of the economics. Our answer to that was, if I make something that's extremely small and compact, it not only reduces my capex per unit, but it also allows me the flexibility of adding capacity over time. Right? If I add capacity over time, what it means is my capital is not locked in on day one, but instead spread over, say, 4 or 5 years. Reaching the same outcome, giving the same output capacities, giving the same productivity, but making far, far better use of capital. And that is something that's required from the Indian market standpoint. Because if you look at, say, the Indian market versus the Chinese market, or say some of the European countries, there are two primary use cases. One is electric vehicles, the other is renewables, right? And as far as battery use case in renewables is concerned, or electric vehicles is concerned, our market is just growing up now. I think we are crossing the 5-6% threshold only now. And as the market grows, you cannot have these large gigafactories, 10, 20, 40 gigawatt hour factories sitting idle because the capital is locked in, right? Instead, if we can match the rate at which this market grows, what it does is it allows us flexibility. Tomorrow, say somebody wants a better cell and we have already developed that better cell. I don't have to, I'm not locked in my capital on one generation old technology. The next module that I add can probably be the next generation of the manufacturing modules also. So that way it allows us flexibility. It allows us to match the requirements of the market. And that is something that we are working on, like proving that cell factories can be modular. It's as new a concept as proving that cells can be three-dimensional.
And your three-dimensional architecture, you've coined an acronym for it, 3DEA, and you also described it in simpler terms to me last time as honeycomb architecture. And can you give us a layperson's understanding of what's the significance?
Okay. Before that, I just want to add a couple of points about where we are from where we have started. Okay. Apoorv talked about the machines. Okay, we are building the machines and how the progression has been. But when we started, we have an idea of the 3D architecture cell. Okay, that is on paper, which also need a lot of refinement over the time. We don't know how to make it. Machines will be needed like based on the kind of processes we require. We have a fair bit of idea like this could be the possible processes, but that is not refined. None of the existing machine can be used here to make our cells. We have done like a multiple iteration to understand, to develop the processes, and how this journey is more complex is that at one hand we have to develop our processes, which is again the machine dependent. If you have a machine, okay, this is the machine I have. Okay, based on that, I can develop my processes or the protocol. On the other side, I have to develop my machines. For that, the process is not fixed. So both the things are go hand on hand. First, we design a process, make a machine, did a iteration. If it fails, we come up with either different process or different machine. Okay, so that way we have done all the development. Now what we have is all the processes. Now we are making our cells in 8 simple steps. Okay, which is like one third to one fourth of the existing cell manufacturing steps. All the 8 steps been perfected out. It's been optimized, and the time required for each steps has been matched. We have the machines which will perform all the processes continuously without any variation. And now we are scaling it up for the next one. Okay. Yeah. And regarding this, our technology, 3-dimensional electrode architecture. When you see the conventional cell, okay, there are 3-4 form factors which are available. I'm not talking about the chemistries, even if the chemistries are different, but still the form factor beneath the electrode architecture is very much similar. Okay, there is not much changes, only the design parameter. Whether it is small format cell like coin cell, which is used, button cells, which are used for different applications or for academic, cylindrical cell, which is mostly used for EVs and storage applications, the pouch cells, which use in our mobile phones, laptops, and some of the EV applications as well, or the prismatic, which is mostly used for EVs as well as the storage application. In all of them, if you open the cell, it has a very thin electrode, okay, which is like a electrode material which is coated on a metal foil. Overall thickness of that electrode is going to be close to 100 micron. Okay. 100 to 200 micron, varying depending upon what is the chemistry, what are the end use. 100 micron is basically the like thickness of a human hair. That is 100 micron. So that's the thickness we are talking about. And the electrode, if the bigger cell, the electrodes are going to be longer, but the thickness of the coated electrode is going to be the same. That is the conventional electrode, whether it is small, whether it is big. When you talk about our 3-dimensional electrode, it is not going to be like a thin electrode. It is not like a coated on any foil. It is like a formed in a particular shape. We build our electrode in a honeycomb design. My anode is a honeycomb design in which it is going to be few millimeter thick. Okay. And we can have like a it could be bigger in the X and Y direction. The area can be bigger. Height is more or less fixed, which is like a few few millimeter. That is my anode. And the cathodes are coming in the form of pins, okay, which is inserted inside those honeycomb architecture. And this is an interlock design where my cathodes are inside the anode, and they are like a perfectly supporting each other, giving the mechanical strength to each other, and that is how the electrode or final cell would look like.
So to explain it, right? So previously what we were doing is, having electrodes like 2 layers of paper sitting on one top of the other, and then you roll up the paper. Now what we are saying is you have a honeycomb which has very thin, very small holes and thousands of these holes in a hexagonal arrangement. And you're having these very thin, very small pins which are individually inserted in each of these holes. And the pins and the honeycomb are now the electrodes. So it's not paper on paper. It is one cylindrical pin inside one hexagon and thousands of these put together.
It's very much similar to the batteries that we were using earlier.
The AA batteries.
AA batteries, AAA batteries. Okay, there is a single carbon rod, and there is my other electrode around it. Okay, you can consider this as the same electrode design, but a miniaturized to a very small dimension, and now thousands of such batteries which are in a parallel manner. That's my 3-dimensional electrode architecture design.
The machines that you have developed now, the output is a full cell like this. I mean, is that how you envisioned it? One end you put in the raw materials needed, out comes a cell, or how does that work?
So eventually that's the vision. And again, like even when it came to the process development, our thought process was this, if I want the most efficient way of manufacturing cells, I need the least number of steps. Now, looking at my design, I need to make the honeycomb. Let's say that's one step. I need to make the pins. That's another step. I need to put a separator between these two. That's a third step. And integrated all of that together, fourth step. That's essentially my stack.
Those are the 8 steps that you're talking about.
So, so there are a couple of steps where you mix the materials, then you make the stack, and then the stack goes into a dry room, you fill the electrolyte and you close the cell. So that's 8 steps, right? I don't want anything more than this, ideally. That's the most efficient way of doing it. I mean, imagine this, right? I mean, when we were in high school and we were taught about, something's a battery, what we had in mind is, there's an anode and there's a cathode. And then there is this electrolyte, and sometimes it needs to be separated. The simplest way we can envision battery manufacturing is you make an anode, put a separator, make cathode, put it together, fill electrolyte, close it. So that's the whole idea. So except for filling electrolyte and closing it, everything happens in the module end to end. And that's the whole thought process. So you can, as part of a factory, you can have multiple modules working on different designs, different chemistries, different mixes, leading to different applications.
And just the folks who might be curious about it, the materials that go into making the anode, cathode, and the electrolyte in your design, what have you decided on?
So as part of the first product, we are working on the LFP chemistry, the lithium iron phosphate. But as a technology, this is chemistry agnostic. We can pretty much take any chemistry that exists today or comes up tomorrow and build cells out of it in this format, this architecture, and the manufacturing process. So today, a lot of talk is going on about sodium-ion batteries. And primarily because sodium is way more easily available as compared to lithium. Say tomorrow the sodium-ion technology or the chemistry is optimized in India. We can just adopt that into our design, into our architecture, and actually start building cells out of it. So as of today, we are working on LFP, lithium iron phosphate, and graphite. again, maybe as of today, these materials can be coming in from China or other places. But there are also people in India who are working on it. And we are working closely with them, trying to understand, how their solutions can fit into our solution and how we can, make this overall an ecosystem play in India and not just a cell play in India.
And in terms of the performance, what are your early findings? You said it'll be 10x better easily in terms of lower heat and so on. What are some of the early findings?
So, currently we are in the development of the cell as a product, so don't have cell level results on that yet. But so we have done individual electrode level characterizations, and what we have seen is the resistance, the internal resistance of these electrodes has come down to as low as around by 55-60% lower as compared to the traditional ones for similar capacity. Our target is 90% lower. So we're still working on that. We're still working on figuring out ways of engineering the materials. So not necessarily making new materials, but get existing materials, but play with them, work with them in such a way that we can actually make composites which deliver higher performance. So we're working on that. So the goal is, I think as of now, we are at 55 to 60% lower. And we should be hitting 90% fairly soon. That's the target we have set ourselves. So it's from there on. It's a fairly standard thing. If the resistance is lower, the heat generation is going to be lower. So that's fairly well understood.
And that's the things we are trying to reduce. It is the heat, that resistance, that is what we're trying to reduce, and we know that heat is just a byproduct of the resistance. So the resistance.
One thing on the materials though. So what we have focused intentionally that we don't want to change chemistry. We don't even want to change the inactive materials. So the kind of carbons that go in as conductive additives, the kind of binders that go in, we have tried to make sure that they're coming from the same supply chains so that we don't face chemistry level challenges. As I said earlier, we eliminated copper, we eliminated aluminum. One change that we have made on the materials front is on the separators. So traditionally, people have been working with these membranes, polymer membranes, plastic membranes. These are made out of polyethylene, polypropylene. And they tended to have a thermal degradation issue above particular temperatures, which we found were the reasons for catastrophic thermal runways, the battery fires, the explosive battery fires that happen. What we have done in our design is we have gone with an all ceramic separator instead of the polymers. And what this does is these ceramics are extremely stable to temperature. They're extremely stable to chemical environments, to electrochemical environments. And hence, the analogy that we like to look at it is the separator is the security guard in the battery. It's the job of the separator to make sure that, one side does not go to the other. Now, in case of a thermal event, if the separator is the first one to run away, the security guard is the first one to run away, who's going to protect the battery? So what we did is made sure that, there's a security guard sitting over there who's so strong that no matter the rest of the building, burns down and crashes down, this guy will be last man standing. So the idea is to make batteries which are so safe that even in case of, an accident, where there was a mechanical failure, there was a car crash, for example, and some of the battery actually got damaged physically. Now, no one can actually build a battery against a damage in a car crash. But what we can build for is that when that car crash happens, that battery gets damaged, the failure should not result in a fire that cascades across the battery and the entire battery explodes. Maybe whatever part got damaged, that can go up in flames. What we look to design for also is, even if it does catch fire, it should be a slow fire, not an aggressive fire. And it should definitely not
propagate into
the rest of the battery packs.
And what are the applications that you are initially targeting for the first commercial product once it's out?
Smaller EV battery packs, so smaller vehicles. Typically, we can look at two-wheelers. So there are some low-speed two-wheelers as well as high-speed two-wheelers. These are smaller battery packs. Also, sometimes in some applications, even 3-wheeler battery packs, as well as something that's coming up now is stationary storage in small battery packs. Because of solar adoption that's happening, rooftop solar adoption that's happening across domestic applications, domestic markets. Now there is room for, or a market opening up for batteries to store this solar energy. Because, let's say someone puts up a 3 kilowatt solar module, something that is getting subsidy today. That's generating about 18 units of electricity every day, but only in 6 hours of the day. So either you sell this to the grid, and the power, the price you get for it is not great, or you can actually store this and use the full energy all through the day, and that actually makes a great use case. Think of it. There's going to be a great synergy when you want to use an electric vehicle and you are charging it at home, and you're going to be charging it at night. But you have solar panels at home which have generating enough energy to charge the vehicle, but it's doing it in the day. How do you cover this gap? So somewhere there has to be storage. So home storage is actually becoming a very interesting application. So that's something we look to target early on.
Okay. As we begin to wrap up, from this point onwards, can you give us a glimpse into your commercialization roadmap? What are some milestones that are going to come up?
Mm-hmm. So 2 things first, right? So we are working on the product. So we work on a product. We work on the manufacturability of the product. So put integrated modular lines, operate those lines, build those products, test it not only internally or with, say, certification laboratories, but also plan to test it with multiple potential customers, get their viewpoints, make sure that the product actually matches their requirements and not what we think are their requirements. Sometimes there can be a gap, so cover that gap. Focus on everything that it takes to make sure that this is going to be manufacturable at scale without issues. So things like quality, things like supply chain and supply chain variances. What happens if the supply chain quality goes up and down? How do we cover for that? How do we prepare for that? So work towards that. Eventually leading to pilot production, commercial pilot production. Put run one modular line, and make sure that that actually the cells actually go into the applications in the market. Say run it for a year or so, gain feedback, which is very valuable in understanding what changes or what improvements do we need to make. And once those are in place and we know that the system is stable and working, that's when we look to expand. So the goal is, current goal is to expand first to a 2 gigawatt hour of capacity. So this could probably happen around 2028, 2029. And then from there on, as the market grows on, we have designed the technology in such a way that, we can actually expand with the market.
So over the next 18 months, what are some really important objectives, maybe even including funding, for example? And I forgot to mention earlier on that you all have opened a new R&D lab, which has coincided with one round of funding as well.
Yes, so we recently closed our seed round of funding. So this was for 27.5 crores. This actually takes us through the product development, the productionizing, proof of manufacturing, build the first line. What we would be looking at this point of time is actually raise a Series A. That would be the capital that takes us to the first manufacturing plant, the pilot manufacturing plant. Run through that manufacturing plant's operation for the, say, as I mentioned, for 1 year. And then eventually start going towards, further fundraisers for larger capacities.
That's it for today. You can find links to e-TRNL's website and its founders' bios in the show notes. If you're an aspiring founder in India, especially in battery energy storage systems, do look them up. I'll be back with another episode of Speciale Focus. Until then, it's goodbye from me, Hari Arakli. Thank you for joining us.